SwayamPrabha. Digital India. Educated India.
In the last lecture, we discussed how we can define the stability of the system based on the location of the poles. And also we have discussed how we can define the type of the system. So in the last lecture, let me rewrite the equation we had. First, let me write the heading, steady state specifications. And we had open loop transfer function, the OLTF Z naught is equal to K bar S minus Z1 dot S minus Cm divided by Sn S minus P1 S minus Pn, and where Gi the zeros in the transfer function and Pi poles of the transfer function. Now we define when n equal to 0, this is type 0 system, and when n equal to 1, type 1 system, n equal to 2, type 2 system. And we can relate the reference signal to the closed loop system, which can able to track. So let me define this equation number 1. Now we can the open loop transfer function with the reference signal to be tracked. Now let's rewrite the equation number 1 as the equation 1 as Z naught is equal to K T1s plus 1 Ta2s plus 1 Tams plus 1, and also for the denominator is to the n Tb1s plus 1 Tb2s plus 1 dot Tbns plus 1. This is basically the same expression, but we wrote in different format. If you take an example, we can write in this above structure how we can write. So for example, G naught is equal to, we have some system S plus 2 and S plus 3, for example. There are two zeros, and we have S into S plus 5 and S plus 8. And if you want to write in terms of equation 2, we can take 2 common and 3 common. 2 into 3, if we take common, we can write 1 by 2 S plus 1, 1 by 3 S plus 1, and if we take common 5 and 8 is 5 into 8. If you write 1 upon 5 is plus 1, 1 upon 8 is plus 1. We can write 2 by 6 divided by 40 we can write TA1S plus 1, TA2S plus 1 divided by S to the S into TB1S plus 1, TB2S plus 1. And where we can write K equal to 6 by 40 and TA1 equal to 1 by 2, TA2 1 by 3, TB1 equal to 1 by 5 and TB2 equal to 1 by 8. So this is why we are written in this form, because for easy analysis will be coming very soon. So this is how we can write the transfer function. Later we'll be discussing, these are basically time constant, but we'll discuss later time constants. In the closed loop system, while we are talking about the closed loop transfer function, what is the main motivation? Basically, we are making the system asymptotically stable, where all the poles of the characteristic equation in the open loop closed loop transfer function should be lie in the left hand plane. So let me write, assuming that the closed loop system of the aircraft, for example, is asymptotically stable, that is 1 plus G naught S. Basically, if you notice, so what the transfer function, closed loop transfer function? We had Cp of S, Gc of S, 1 plus Gp of S, and Gc of S. So this is denoted by G naught of S, right? So, and further we can write Gp of S, Gc of S, 1 plus G naught of S. So the characteristic equation basically of the closed loop system 1 plus G naught of S equal to 0 only has roots with negative real parts. So if the poles, the roots we are getting from the characteristic equation, these are basically poles, and the negative, the real part of the poles should be negative in sign, and then we can say that system is asymptotically stable, because system will be decaying to some point reference signal. Now we can examine the steady state error for the different test signals. As you have done before in the earlier lecture, I mean, in the beginning of this course, we discussed two important terms. One is the final value theorem, and second is initial value theorem. So now we are going to use final value theorem, how we can define the system goes to the steady state value. So system goes to the reference signal. What is the error between the, basically if you look the response, this is my desired response. So we are going to find the dotted line, basically desired response, and this is basically actual, right? Actual, and the dotted line is actually desired one. So using the final value theorem, we'll be finding how we can find the error between desired value and final value. Between this, how we can find the error between this. So now this steady state error we can define by ESS in frequency domain, sorry, in time domain, it will be limit t tends to infinity e of t for any signal as time tends to infinity, what is the final value? And from this, we can write, if you write in Laplace domain or frequency domain, you can write is E of S. This is already you have done. And from this further, you can write limit S tends to 0. What is the expression for ES? Already we had in the last lecture. ES expression. So ES expression we had 1 upon, if you remember, 1 upon 1 plus G naught S into RS. So now for the different test signal, how we can find the steady state error in the system? So now I think the problem is easy now. Let's examine the steady state error for the different types of reference signals. Let's start with the step input. This is the most important one we use very frequently in the control system design. So step input, we'll assume, and the Laplace transform of step input, we know R of S equal to 1 upon S, where R of t equal to 1. Applying final value theorem, let me define this equation number 1, equation number 3. So applying any final value theorem, ESS we can write limit S tends to 0, S by 1 plus G naught S into 1 upon S, because RS equal to 1 upon S. And here S is cancelled, we can write 1 upon 1 plus limit S tends to 0, G naught S. So if you know the open loop transfer function of the system, we can get the steady state error for a reference signal. So here we can define the term limit S tends to 0, G naught S be denoted as KSP. So here KSP we can write limit S tends to 0, G naught S. This is called static position error. If you substitute this expression in steady state condition, or the steady state error condition in equation 4, we can write ESS 1 upon 1 plus KSP. Now let's look how the type of the system will influence the error in the system. Now let's consider the type 0 system. For a type 0 system, where n equal to 0, we can find KSP, because KSP is a function of open loop transfer function here. So we know limit S tends to 0, K into, if it is type 0 system, then there is no open loop poles in the system. So S to the n will be 1. S to the n will be 1. So we can write K into TA1S plus 1 Ta2s plus 1 dot 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 TAMS plus 1. And the denominator part, since there is no force at origin, we can write TB1S plus 1, TB2S plus 1 dot 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 TBNS plus 1. This is how we can write. Now, if you put S equal to 0 here, so this value yields to be K. Simple this K. Very interesting conclusion from this part we'll have. Now, so what is the takeaway from this part? So if the type 0 system is there, and if you are applying a step input, then ESS will be 1 upon 1 plus K. So there exist steady state error. Very interesting. So if it means that if the system is type 0 system, and if you are applying step input as a reference signal, there will be error, and this is the magnitude of the error in the system. Now let's look for type 1 system. For type 1 system, or let's assume higher order system, n is greater than 1. So we can write KSP equal to limit s tends to 0, K TA1 S plus 1, TB2 S plus 1 dot 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 TBM S plus 1, and in denominator, since we are assuming higher order, so we can let's write S to the n, and TB1S plus 1, TB2S plus 1 dot 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 TBNS plus 1. Now, if you put S equal to 0 in this case, here in the limit, so this part going to be infinite. So let me write then. Therefore, for type 0 system, the steady state error to a step input cannot be neglected. Completely, because we have seen this is the error for type 0 system. But if it is type 1 and higher order system can track step input perfectly. Very interesting. And the steady state error, we can write ESS equal to 1 upon 1 plus infinity is going to 0. So it is completely tracked. Track means is going to 0 means y of t goes to r of t, reference signal. So what is the takeaway from this part? So if the system is type 1 or a higher order system, if you are having reference signal step, then it can be perfectly, we can matches y of t to r of t. So steady state error can be reduced to 0. This is the takeaway from this part. So this is the part for the step function. Now let's look the ramp input. If you're having ramp input in the system, what will happen? Ramp input. Applying the final value theorem, apply the final value theorem, we can write ESS equal to limit s tends to 0 s by 1 plus g naught s into rs. And if you substitute for the ramp input, you know, r of s 1 upon s square, where rt equal to t. This is the ramp input. And if you substitute here, limit s tends to 0, limit s tends to 0, s by 1 plus g naught s into 1 upon s square. So you'll get limit s tends to 0, 1 upon s plus s g naught s. Or we can, if we put s equal to 0 here, the first term we can get 1 upon limit s tends to 0 is g naught s. Very interesting. And let's denote this term, the static velocity error constant KSV equal to limit s tends to 0 is g naught s. So the denominator part we defined by KSV, which is basically a static velocity error constant. Now, so in terms of steady state error, we can write steady state error, we can write 1 upon KSV. Now we'll look the type 0 system first. For a type 0 system where n equal to 0 and KSB, we can find limit s tends to 0. We know K, it should be Ks Ta1s plus 1 Ta2s plus 1 dot 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 Tams plus 1. And the denominator, since it's type 0 system, there is no poles at origin, we can write Tb1s plus 1, Tb2s plus 1, and Tbns plus 1. If you put s equal to 0, this expression goes to 0. And so what is the takeaway? So here, your ESS is 1 upon 0 and it is infinite. So if the system is type 0 system, and if you are applying a ramp input, there will be infinite error in the steady state. So we can't apply. Now let's look the type 1 system. For a type 1 system where n equal to 1, let's look. KSB, we can write limit s tends to 0, K s Ta1 s plus 1, Ta2s plus 1 dot 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 Tmm plus Tms plus 1 divided by, since this is type 1 system, there is one pole at origin, so we can write is Tb1s plus 1, Tb2s plus 1, Tbns plus 1. This is cancelled, so we can write, if we put s equal to 0, we have k. So what is the takeaway from this? So steady state error, we can write 1 upon KSV, which is 1 upon k. So if the system is type 1 system, and if you are applying ramp input, there will be steady state error. steady state error. Very important conclusion from this. Now let's look the type 2 or a higher order system. For type 2 or higher order n greater than equal to 2. So let me write the case B. We can write limit s tends to 0 is TA1, K will be there, anyways, and TA1 is 1, TA2S plus 1, TAMS plus 1 divided by, since it is higher order system, we can write s to the n, TB1S plus 1, TB2S plus 1, TS plus 1. Now, if you put s equal to 0 here, 1s will cancel out. So I can write in place of s to the n, I can write s n minus 1. So now, since it is higher order, n greater than 2, so if you put s equal to 0, the value of KSB goes to infinite. So in this case, very important takeaway. Therefore, the error, steady state error, is goes to 1 upon KSB, 1 upon infinity is going to 0. So what is the takeaway from this part? If the system is type 2 or higher order system, and if you are applying ramp input as a reference signal, there will be no steady state error in the steady state response. So this is how we can choose the different type of signal to be tested in control system. This is very, very important takeaway from this lecture. And now we'll be taking an example, then we'll conclude in this lecture. Example. Let us assume our PD controlled aircraft attitude system. We know GP of S 1 upon I S square plus KDS. This is already have found before. If you modify the PD control, and this is the plant transfer function in the inner loop we had. So now we can write this expression as KD is 1 upon KD S plus 1. And the controller transfer function for this particular case, the controller transfer function, if you remember, transfer function, we had GC of S equal to AP. And the open loop transfer function, the open loop transfer function, we can write G naught of S equal to GP of S, GC of S equal to, can write KP divided by KDS 1 by KD S plus 1. Now, this is quite clear. The system type from this, the type of the system of G naught S is 1. And now let's look how the system going to respond to the different reference input. First, let's try with the step input. R of S equal to 1 upon S. And first we'll find the static error constant KSP, which is basically limit h tends to 0, g naught of s. Now if you substitute limit h tends to 0, g naught in place of g naught of s, if you substitute the expression Kp divided by Kd s 1 by Kds plus 1, so we have the value is infinity. And the steady state error ESS we can write 1 upon 1 plus KSP, which is 1 by 1 plus infinity is equals to 0. And from this we can say we can track step command completely. Now let's look with the ramp input. So for the ramp input, the static velocity error constant, we can write KSP equal to limit s tends to 0 is g naught of s, and if you substitute in place of g naught of s, Kp Kds 1 by Kd s plus 1, and here s is cancelled, so the value goes to Kp by Kd. And the steady state error, we can have ESS equal to 1 upon KSP, which is nothing but Kd by Kp. So this is basically non-zero steady state error. For this particular aircraft attitude control system, if you apply ramp input, we will have steady state error in the response. But if you apply step command, the reference signal, we can come up with 0 steady state in the response. Let's stop it here. In the next lecture, we'll be discussing how we can consider the disturbance in the system and how it is going to affect the steady state error.